May 20th, 2015. Poster presentations.
Quadcopters to get aerial photographs to make 3D. And we also use
Just go around so you can see all of them.
With proper rules and updated data.
to like survey the body using sonar. Yeah, just type of map.
That was cool.
That's so impressive. I can't even.
I'm gonna go eat. So that looks interesting. Thank you.
And on the side, we have Tony at Stony Brook University. Brian at Beth Israel Deaconess Medical Center. Nicholas did his at Princeton last summer. Princeton, working with the University of Hawaii. And Julia did hers last summer at the University of Minnesota. We have Kevin, who's going to be working in ID. Who are you?
Oh, I'm Sophie. And this summer I'm going to be at Woods Hole, which is on Cape Cod in Massachusetts. And I'll be working with a professor who focuses
So I'm focusing in on this. Is this the professor?
No, this is not the professor.
Oh, okay.
This is another engineer who works with him. But he focuses on mapping coastal movements. And he uses two main tools to do that. One of them is aerial crafts, quadcopters, to take photographs and to use those photographs to make 3D topographic maps, as you can see on the left.
Yep.
And the other tool he uses is his own invention called the jet yak, which combines like the body of a kayak and the engine, the jet engine. And it has sort of sonar that picks up the topography of the bottom, and we can use that to model the seafloor. This is a video about the making and using of the jet yak. This is specifically about a project that they did in Greenland with glaciers.
Is that a jet yak right there?
Yeah, that is the jet yak moving. Maybe we can bring it back to the front.
No, that's okay. Okay. Thank you, Sophie.
Thank you.
Okay, you're on.
Hey, I'm Sam Caccavelli, and this summer I'll be doing an internship with a company called Silent Systems.
Here, let me go in.
did it after I did it.
The goal of Silent Systems is to create a new form of endpoint protection or security on a closed network, like a laptop or a business or your home potentially. And the way they're looking to do that is completely new to the world of cybersecurity, and it's by creating a system, antivirus system, at the hypervisor level of a computer, which is the level below your OS runs, your operating system, being Linux, Windows, or Mac. And the benefits of this is that theoretically nothing can go, no program can run without accessing the hypervisor level, meaning that there's no way around this sort of antivirus. Specifically, what I've been doing to lead up to this is learning a lot about Linux and Linux kernel, the Linux operating system, and the Linux paging system, the way it's dedicated to virtual addresses to physical memory addresses. And so a few of the examples up here are programs that I've written.
So I'm going to zoom in. So what do we have here? Sort of point it.
Up here we have a make file, so that's a typical C file that dictates how
Right?
C programs are built.
Yeah. And then below.
Right here actually, is the command window. That
here's
is the
command
typical
window.
output that you get when you make a C program.
Yep.
And then this longer program is a program that takes some sort of address, a
Yep.
virtual memory address, and gives you the actual physical address of the data on your computer.
Yep.
And the terminal window right there is just a simple explanation of it doing so.
Okay. Where's Silent?
Silent Systems is located in Boston, right near International Place and South Station.
Okay. Thank you very much.
Thank you.
Go. This is Carly.
I'm going to be working at the Lab for Playful Computation this summer, which is a part of a Tufts program called the Center for Engineering Education and Outreach.
Sorry.
So they're working on kind of studying how children learn STEM and how they can get children to learn more efficiently and be more interested in like engineering and STEM and computer sciences. So they have a couple of projects going on at the moment. Trails Forward and Locky Talkie are two really cool ones. So I'm going to be helping out with those some this summer.
So one of the domes in the observatory.
This is
And it
Dunstan
has a
Cone.
diffraction grating here that splits light from the point that you see in a star to the rainbow that you see on the left-hand side. And what you actually see is a variation in the intensity based on the wavelength, which tells you what the elemental composition is. So for example here, this is a spectra of Sirius, and you can see hydrogen alpha, beta, and gamma lines, which means that you can see hydrogen in Sirius, as there should be. And the plan is to take the spectra of all the stars that are there and write books and
Okay, here we go. Orion Watson.
I'm Orion Watson, and I will be filling a protein scaffold as a reference.
Well, I'm going to go over and just go through this.
Which means that I will be taking proteins that have been sequenced, but their sequence is incomplete or scrambled, and writing an algorithm that attempts to fix that and put them back in complete forms based on similar proteins.
All right, and where are you doing this?
Montana State University.
Okay. And so you're going to be writing programs, what language?
C++.
Okay. And what do you have on the laptop there?
This is the professor, Dr. behind you, who I'll be working with. Him and a graduate student.
Sorry, what's his name?
Dr. Ju.
All right. Thank you very much.
I'm Kevin.
And what are you going to be doing?
I'm going to be doing an internship at IDEO for a month over the summer. I create other companies too.
Can you describe some examples of stuff they've done?
Okay, so some examples that I have up here are
Yep.
they helped to develop one biotech company's development of needle-free vaccines, and that's still waiting to be FDA approved right
Okay.
now. And then there's this other one which is helping. Another recent one was helping IKEA come up with a futuristic kitchen table. Which uses all kinds of dynamics and stuff with
Is that an
specialized
actual stove?
Yeah, this is taking
zoom
examples of one of the things that it would potentially have the ability to do is weigh the different things and tell you what kind of stuff you can use the ingredients for, as well as heat and everything, and look at stuff online for
incredible.
shopping.
All right. Okay. Thank you very much.
No problem.
Hi, my name is Tony. I will be doing an internship this summer at the Simmerling Lab in Stony Brook University on Long Island.
Stony Brook, application free.
It's the lab of Professor Carlos Simmerling. For molecular dynamics, it's a computer-based simulation of atoms so that you can simulate biological processes like protein folding and the ligand-protein interactions on the computer. You do that by inputting the coordinates of all the atoms, the types of the atoms, and specifying a force field. So the atoms will move according to Newton's second law as precise by the potential that you give using the force field. Amber describes the force on an atom based on the bond length of the atom with its surrounding atoms.
Who are you?
Nicholas.
And what did you do last summer?
I worked as part of a research team at Princeton University in the architecture department, working to design this project. So the entire summer we spent researching a variety of factors that influence the way humans feel heat, how we can alleviate that. And this resulted in something we called the thermohelodome, which was this styrofoam 8-meter in diameter dome here.
That's 8 meters wide. So you can walk into
Did you make
that.
this?
Yeah, definitely.
Yeah.
It's designed to hold a decent sized group of people inside.
Okay.
And the goals of the research were to create a cool outdoor space without having to seal it off and use air conditioning, and to test the hypothesis that radiant heating can be redirected through IR reflection, which is effectively using a mirror for heat.
Thank you, Nick.
It's mostly on endocrinology system and how we can use insulin and engineer hormones to control diabetes and I guess
Okay.
fix it for people.
Okay. And what do you have here? I'm just going to zoom in for a sec. So it's at Beth Israel. There's the professor, Professor Kim. No relation.
No relation.
Okay.
And so insulin is the hormone that metabolizes all your food and turns it into energy. And diabetes is kind of the lack of insulin or the lack of metabolizing those energies. So it can lead to health problems. So, and people are sometimes born with lack of insulin or too much insulin, and that can be a problem because it's unbalanced. And our lab focuses on how we can control or give and extract insulin from people. And if it's too much, how do we take it out? If there's not enough, how do we put it in? And how we can genetically engineer insulin to make it more efficient and more helpful for the people who need it. And right now we are thinking about like ways we can technologically inject it, or we can genetically inject it. So we can So we can try to engineer the pancreas somehow that can create an excess or decrease the amount of insulin it creates on a daily basis. And that's what we're researching, if it could actually do that, or we still need technology to do this.
Thank you very much. Who are you?
Brian.
Yep.
I'm going to be working at MIT this summer. I'm going to be working at the Center for Transportation and Logistics.
Yep.
And so what I've been looking at leading up to this summer is hubway data. So what they're looking at is the use of bicycles in passenger and freight transportation.
Okay, I'm going to zoom in on this. Just so you said hubway.
Yep. And Hubway is a bike sharing system in Boston. And it supplies data that tells us about people's use of bicycles and how that can be relevant to its implications in passenger and freight transportation. So the CTL is composed of approximately 15 labs. It's a substantial amount. There are approximately 75 MIT faculty that work there. So it's a relatively large center.
Yeah.
And they're focused on how they can make supply chains more efficient. And so, this, as I said, this summer I'm looking at the specific part of how they can use bicycles within that.
All right. Okay.
I'm Julia Hill.
And what did you do last summer?
I spent the last summer at the Medical Device Center at the University of Minnesota. And I worked with a team of about 6 or 7 undergrad and grad students there. And there were about 4 or 5 other groups of about the same size. And we all got tasks from doctors at the hospital at the University of Minnesota to design a device to solve a problem that they see every day.
Okay. And the poster has an example of a problem.
Yes. We had a doctor come from Women's Cancers. And she was looking for a device that would solve the problem of tissue stenosis after radiation therapy. Basically, the tissue gets extremely rigid and can shrink in size, so we were looking for something to help combat that, both because it's painful and just to keep the general dimensions of the body.
Yep. And the photos on the right, are those what you actually came up with?
That's the device we printed.
Can you kind of point out what they are?
It all goes together in one. So this fits in the bottom right here, and this valve goes in.
Okay.
And you use a little syringe kind of thing. In total, this whole thing is about that big.
Okay.
And you use a syringe to go into this valve right there.
Okay.
And it blows up this balloon.
Yeah.
And the balloon is inside of this top piece. And so as you blow up the balloon, it expands. And that means that the device has a variable size.
Okay.
So it can get both longer and wider.
What were the results? How has it gone? What are you getting in terms of feedback on this device?
Right now, the technology is up for licensing, and it has a patent pending in America. It's gone pretty well. The device is pretty much the only one of its kind. We spent a lot of time researching patents available on the market, and there was really nothing like this. So it's kind of a new way to approach this problem.
Okay. Thank you very much.
You're welcome.